So this is the final session of the day, and it's going to go until however long it takes, till 4:30 or so, and then after that is dinner. So yes, it's the AFLOW team, Coriosis, David Hicks, and Cormac Toher. And Corey is here in person.
Yeah, like the session here, our talk will be hybrid as well. So I'm the in-person representative of AFLOW. I'm not going to say too much more because Cormac's going to do the introduction. But we were all previously localized at Duke, and now we're all in different places. And so yeah, I'll pass it over to Cormac Toher now, and he'll do the introduction.
Okay, thanks, Corey. Everybody can hear me, or yes? Okay, so thanks, Corey, for the introduction, and Ichiro for the introduction. So yeah, so we're going to have the next 2 hours, and there's going to be three of us speaking. I'm going to go first, then it'll be David Hicks, and then Coriosis, and we're going to be talking about different aspects of the AFLOW infrastructure for computational materials discovery. Like I mentioned, so as Corey mentioned, we were all previously part of the Stefano Curtarolo's group, so the Center for Autonomous Materials Design at Duke University. And now I'm an assistant professor at University of Texas at Dallas. David Hicks is now a research scientist at a company called Lyft. And Coriosis just recently started as an assistant professor at Johns Hopkins University. So like I said, we're going to be have three different sections. So the first section, I'm going to talk about going to give an introduction to AFLOW. Going to give an overview of the AFLOW database, how you can search for different materials online using the AFLOW web portal, and then I'll talk about different other ways to access the database, particularly the AFLUX Search-API. Then in the second part, David Hicks will talk about some online tools for doing things like symmetry analysis, for decorating AFLOW prototypes, to generate new materials, and also to do AFLOW Excel Finder, which allows you to both extract prototype information from materials and also then to compare materials, find unique materials, etc. And then in the last part, Coriosis will talk about the AFLOW ML online application. Okay, so then before that, I'm just going to talk about before I get started, I'm going to talk about some brief tutorial logistics. So I think everybody's reasonably familiar with Zoom at this point, but we're going to have, so we won't sort of go into the breakout rooms as such, but there is a breakout room open. So if people do have problems, I just suggest putting a message in the chat. If we're not able to solve it over the chat, then one of us can go into a breakout room with you. So we have two TAs who are available who will try and do technical support for issues with Zoom or Colab, while we'll also have an AFLOW support room. Then one of us, or me or David, can go inside with you if you have questions about the AFLOW tutorial, if you're having problems using performing some of the exercises, for example. So if you do have a question, then please send a message in chat, and we will try and answer it, or else someone will go into a breakout room for you. For Google Colab, I don't know if we had issues with this before, if they've solved these issues, but historically we've always found it works better with Firefox or Microsoft Edge. Historically, Chrome has had some issues displaying images. So if you're having problems with Google Chrome, maybe try using a different browser. So then, just to give a brief introduction of what kind of materials we're interested in, why we do this. So some of the materials applications we've been looking for, things like thermal barrier coatings, for example, for turbine blades inside jet engines. We're for super hard wear-resistant coatings for machine tools. We've looked for biocompatible coatings, so specifically corrosion-resistant alloys for biomedical implants. Then we haven't really done so much focus on this yet, but there's also work being done on photovoltaic materials for solar energy harvesting, solid-state electrolytes for lithium-ion batteries, as well as things like superconductors or heat sinks for advanced electronics. And so if we want to explore material space, just to give you an idea of the size of this problem, if you look at all the different materials you can form from pairs of elements. So if you take about these elements, so the non-radioactive, non-noble gas elements, you have about 78 of these elements. If you look at the ways you can combine pairs, it's about 3,000. If you look at the way you combine triplets, it's about 76,000. By the time you get up to quaternaries, you have some like over 1 million alloy systems. By 5 component systems, you have 20 million. 6 components, you have 250 million. And this only takes into account like pairs, combinations of elements. So this is just like basically material systems. You actually got individual materials. If you take into account different structures, different stoichiometric ratios, etc., we find that, and if we look at all the different prototypes or all the different unique structures that we've identified so far, we get, and look at all the ways you can decorate them, we get something like 10 to the power of 177 possible different materials that you could make. So obviously this is way too much to do by hand. So that's why we've started doing automated materials discovery. So what we do is when we start our calculations, we either start from an experimentally observed structure, so something that's already been previously experimentally observed, for example, in the ICSD. So then we're looking to calculate additional properties of this material, or else we use what's called structural prototypes. And Dr. Hicks will talk more about this in the next part of this session. So then these are just sort of different structures that you can then decorate combinatorially with different elements to form new hypothetical structures where you can really try to do materials discovery. So then when we take these, we take these new structures, we form DFT calculations on them. So we use AFLOW, which then automates the VASP calculations. Then we pipe the results into the AFLOW database. And then we interrogate this database either to find new candidate materials for specific applications, or we use the data that we've generated to build thermodynamic models or machine learning models. So the way AFLOW works is it wraps around the DFT code. In our case, we're usually using VASP. So then AFLOW, it generates either one input file, or you can generate a whole set of input files. Then this sets up different DFT calculations. It monitors the DFT calculations. If there are errors in the DFT calculations, it can adjust the parameters. So it has some library of, say, if it sees a certain error, it knows that, oh, we need to adjust this parameter to try and get the calculation to converge. And then once the calculations are finished, it then extracts properties. So for example, it will extract things like the electronic band gap. It can plot the band structure along the high symmetry paths. And we can combine multiple DFT calculations to calculate things like thermal properties or elastic properties. And finally, it pipes the results into a database for online storage and dissemination. There's a couple of quick questions in chats. Yeah. Okay, Corey's already answered it. Okay, so then the data itself is accessible at the aflow.org web portal. So if you go to aflow.org in your browser, you'll see this web page. So this is the top of the web page. So there you can see some details about like what kind of data we have available. So we have over 3.5 million materials entries with over 700 million properties. Then you can see a breakdown of different types of properties we have, how many band structures we have, how many elastic properties, thermal properties, etc. We have then we have other links to other information. For example, here we have our AFLOW schools and seminars page. So you can see recordings of previous schools. You can see also a list of upcoming seminars that we host as part of this at the Center of Materials Design. If you scroll down a bit further on the page, you can see different applications. So later on, Dr. David Hicks will be going through this AFLOW online and showing you some tools that we can use in here to perform symmetry analysis, as well as in this crystal prototypes tools. And Dr. Rosas will be showing you this AFLOW online. But here we're going to look at the MLMR search to show you how you can access the data. So if you go to this search page, this advanced search page, you see a periodic table. So this obviously allows you to select specific elements. Select specific elements. You can also select groups of elements. So for example, you could select all the alkali halides if you wanted to look for that. Then you can do things like set the number of species, so restrict the number to a specific number of species, and you can also perform logic operations like AND operations, NOT operations, and so on. So then you also have a slide to property filters, or you can bring up the property filters onto the search page. I'll show you that's here. So if you click on this display button, so you click on this option over here, it will bring up also a set of property filters. So you see electronic properties, magnetic properties, mechanical properties, and so on. So here then you can select specific elements. So here's an example. You add, here we've got adding sodium and chlorine. We've also then set the number of species to 2. So we only look for sodium and chlorine, and we don't see other elements as well. We can also add filters. So in this case, we've added the electronic band gap filter, and you can also set a specific range if you want. So you can set, so you can then check this box to restrict filter results to a specific value range. So I'm just going to switch over now. I'm going to stop sharing this slideshow and I'm going to switch over to the browser. So I'll just work a few examples, and then we'll move on and we'll try a couple of exercises. So let me share my browser. So let me pick that one. Okay, so hopefully you'll see now my browser with the AFLOW page. So again, here we have our different, the number of materials, number of properties. So number of things like elastic properties, thermal properties, etc. And if we scroll down along the page, we get to this MLMR search option. So then we can click, we go in here, select on this, it'll open up a new tab. And here you see the search page. So again, we can toggle between the different displays. So here we display only the elements, and you can then switch to the property filter window like this. So you can switch back and forth between the periodic table and the property filter, or you can click on this button up here, and this will bring up both displays on one page, which personally I prefer this option. So then let's say we want to look for different materials. So let's look for, titanium oxides. So look for titanium, titanium and oxygen, and then we do a search for things with 2 species. So now we just want to look for titanium oxide, and now we want to look for the electronic band gap. And this time, instead of just looking for all the values, we want to restrict the value. And let's say we want something between, let's say 2 and 8 electron volts. So here we do a search in the range from 2 to 8 electron volts, and then we hit search. Okay, and this will bring us up our results. So then you can see here, let's list the smallest value first. So this is from smallest to largest. Well, here we can toggle, actually we can sort. So if we click this button, now we get the smallest values first. If we click it again, we get the largest values first. So let's try sorting it like this. So we get the smallest value first. And then we can look at the first entry here. We can click on this entry. And we can bring up this entry here. So one of the things to note here is that if here we've selected the default here is to select ICSD only. So this selects only existing materials. Whereas if we were to click all of AFLOW, we would search the entire AFLOW database. So there's 2 main parts to the AFLOW database. There's the ICSD part, which is sort of based on existing materials that we just calculated additional properties for. We have about 60,000 entries. And then this tends to have additional data calculated for it. So usually has electronic band structure calculated. It has things like, it might also have thermal and elastic properties are often calculated for these materials. Then we have all of AFLOW, this is all of it, including the ICSD, but most of this is built on the basis of structural prototypes. In this case, we're mostly interested in thermodynamics and trying to figure out which materials might be possibly synthesizable. And in this case, we generally only focus on calculating thermodynamic properties. A lot of the time, we won't necessarily have electronic properties or thermomechanical properties calculated for these materials. So I'll just show you, if you click on one of these, so then to look at these individual entries, if you look at this entry page here, if you select this one, let's open up the page. Clicking on the label, we can see that some of the information we have. So we have a structural visualization, which you can interact with, you can view from different angles, you can build supercells, etc. Scroll down, you get some structural information. You scroll down further, you get some things like the electronic information, so beta charge distribution, beta charge analysis. And then you get electronic properties and you see the electronic band structure. And then at the end, you have things like calculation details, so like the energy cutoff or the K-point grid. And you have some downloadable files, particularly things like the structured geometry files. Okay, so let's do another search. This time I'm going to do something a bit more complicated. Let's see if it works. So let's say I want something that is tin, but not lead. Okay, and I want to look at, let's say, ternary materials. And this time I want to look at all of AFLOW. And this time I'm not interested in electronic band gap, but maybe I want to see things that have space group 225. I put it in here. So we only look at the materials that have space group 225 that have tin and not lead. And let's look at binaries. Let's do a search. So this might take some time because this is going to have quite a lot of entries. So it finds 429 entries. So here you can see we have a lot of tin alloys with this 225 space group. Okay, so let's see if there's a few questions in the chat. Okay, so the first question in the chat is about covalent organic frameworks. So this, we don't really have organic materials in the lecture. So as Corey mentioned in the response, we don't really have organic materials. This we mainly focus on inorganic materials for this database. Okay, so unless anybody has any other questions, I'm going to now bring back up my PowerPoint slides, and we're going to look at some exercises. So we're going to take maybe 5 minutes, and people can try doing the exercises themselves. And then we can go through them afterwards together and see how it works. And if anybody wants any problems or any questions, just put a question in the chat. My screen. Okay, so first exercise is to use the advanced search functionality, find the band gap for silicon carbide in the zinc blende structure. So space group number 216. So again, you want to look for silicon and carbon. You want to have 2 species. You want to look, and you want to then restrict the space group to be number 216. And you want to find the band gap. So you want to search for electronic band gap values. Then the second exercise is to use the advanced search functionality find materials containing tin but not lead, with band gaps between 1 electron volt and 3 electron volts in the ICSD catalog of the AFLOW database. How many results are returned? So let's take about 5 minutes or so to try this. If anybody has any issues or any questions, just put a question in the chat and we'll try and respond. Okay, thanks, David. So yeah, so let's start going through these exercises. So first exercise was to use the advanced search functionality to find the band gap for silicon carbide in the zinc blende structure. So space group number 216. So let me stop sharing my screen and I'll bring up my my web browser so we can do the example. So share. Okay. Here we want to relook at the ICSD. So let's clear this selection. So reset the search. So you want to look for zinc sulfide. So ZNS, these are 2 species. And we want to look for the zinc blende space group. So we go from 216 to 216. And then we should look for the electronic band gap. We don't want to restrict the value because we just want to find out which one is the smallest or largest. We just want to find out the value. So let's do this search. So here we can see the results. So here you can see this is the zinc blende structure with this 216 space group. And you can see the electronic band gap value is 2.68 electron volts. So let's clear this. So now we want to look for the ICSD catalog and we want to find materials containing tin but not lead. So here we have tin but not lead. Lead. Here we don't want to specify the number of species. And we want to look for materials. We don't want to restrict the value of the space group, but we do want to restrict the value of the band gap to be between 1 and 3 electron volts. And then we're going to do a search. So here we can see that we found 369 entries, and you can see you've got ternaries, quaternaries, and so on. So when you don't restrict the number of species, AFLOW will look at whatever materials satisfy whatever search query it is, but it will also keep, unless you've specified not to have a specific element, it will include all other elements that aren't listed in the search query. So that's why if you're looking for a specific material, so for example, if you wanted just sodium chloride, it's pretty important to specify the number of species up here. Okay, so then let's go back to the slides. Zoom. Okay. Okay, so I showed you before is how to access things by hand. So this can be it's useful if you want to just look for a few different materials, but if you want to build up large data sets, for example, if you want to train something on machine learning, then you want to look at things that you can do more programmatically. So you can download the data, for example, in a JSON format or something like this, so that you can really use it as an input for a machine learning model, for example, for training machine learning. So to do this, we took our aflow.org webpage and we exposed the underlying search programmatically. And we did this using the AFLUX search language. So the AFLUX search language, enables the search functionality through the query part of the URI. So we have our search server, so it's https://aflow.org/API/aflux. So that's the API server. And then we have the query part, which consists of, this bit after the question mark, and it consists of a matchbook and directives. So the matchbook are materials, keywords with arguments. You can get a full keyword list. There's a couple of different ways. You can either use this help directive and search with the argument properties, or you can use the keyword schema. And both of those will bring up a list of different of these materials properties keywords. Sorry. Then we also have directives. So these are formatting instructions with arguments. So as well as the help and schema directives, you also have things like formatting directives. So if you want to return the data in JSON format, which is the default format, or in HTML, you can also use, there's also a paging keyword, which controls the number of entries and the page number displayed. So by default, it will display the first page of 64 entries. So you have 64 entries per page. So then if you have paging 2, you can get to see the second set of 64 and so on. And we'll go through a bit in more detail how to do different types of paging directives and when we work through some examples. AFLUX can also be used with any language that can be used to query URLs. So for example, if you want to do these search queries with Python, and we'll work through some examples with Python later on as well, you can use this minimal Python script. So again, here we have our API, we have our matchbook, our directive, then we build up our request by combining the API, the matchbook, and the directive, and then we get a response. So we use this JSON loads response that will convert this JSON that you get back into and this will load it as a Python dictionary, and then you can sort of extract data from the Python dictionary and reformat the data into the format that you want yourself. So AFLUX supports the use of several logical operators. The operator scope can be inter-property and or intra-property. So we have these block operators that are defined by these parentheses. So this basically sets the scope, and you can control the order in which things are executed. We have an AND operator that's represented by a comma, an OR operator is represented by a colon, a NOT operator is represented by an exclamation mark. Then we have this loose or wildcard operator that allows you to search for value ranges. And I'll show you how that works with some examples. And then you can also do string comparisons. And so you can look for specific values. Specific. So if you wanted to find string values within the database. And then there's also a mute operator that's represented by a $sign. So if you want to query on some property, but you don't necessarily want that property returned in the data set, then you can also mute it using this $sign. And we'll show you some examples. Okay, so now I'm going to switch over to so we're going to work through some examples. And to do this, I'm going to use the Colab notebooks. So if you open up the Colab notebook, that should have been shared with you. If not, I can also or maybe Corey can add the address in the chat directly so if people want to open it up. So let me stop sharing this and I'll share my Colab notebook. Share. Okay, so now you should see my Colab notebook. So once you open this, if you want to be able to actually run anything in it, what you'll need to do is you'll need to go to File. So you've probably done this already with the Colab notebooks, and then save a copy in Drive. And this should open something in a new tab. So open a new tab. And now we have a Colab notebook that we can work inside. So at the top here, we just have, again, the introduction. So the list of operators. So this stuff I've already gone through. Here's an example. So if you want to look, for example, for a, this shows how these operators work. So in this case, we have this query is for species. So it's sodium or potassium and chlorine. So this we're looking for sodium chloride or potassium chloride. And species is 2. So just sodium chloride and potassium chloride. And we want a band gap. So this is the loose operator between 1 and 5 electron volts. And we're also going to get back information on the energy per cell. But let's work through some more detailed examples. So the first simplest example is if you put in this query with no keywords at all, just a question mark, this will actually give you some basic help text. So if you have your Colab notebook open and you've made a copy, you can try clicking on this arrow in the corner to run this cell. So here we're using CERL just to run individual queries. You can also take these queries and put them directly into your browser window, and you should also be able to get some results. So this again just runs through some examples, explains the different operators, and this is sort of a basic intro overview help page. that's in plain text, but it's actually in the form of a JSON list. Then if we want the list of matchable keywords, here we can use either the help properties that we saw before, or we can use this schema keyword. So again, this will return this in a JSON format. So again, we get a full list. So if we scroll up to the top, yeah, so you can see different types of keywords that we have here. So here we have pressure. So here's an example: positions fractional, positions Cartesian. So this gives the positions of the different atoms in Cartesian coordinates, and it will tell you things like the type, the units, etc. Let's keep going down. So now let's look at some different operators. So here we want to look at this is just the AND operator. So here, like I mentioned before, we have different catalogs or different groups of data. So here we're looking for in this ICSD catalog. So this is just these entries that have already been run. So we're looking for compounds containing chromium and 3 total species. So its species is chromium and species is 3. And here we're looking for the first page. Paging is 1. So we're going to get the first 64 entries. And we'll go through the paging command a bit later and show how you can adjust the number of entries per page. So if we run this, we get ternary compounds containing chromium. So you can see here the first entry is an oxide. So let's say we want something that doesn't contain oxygen. So then we can say not oxygen. So now we're excluding oxygen from the results. And here you can see that the results have reduced. So here we had 862 results. Now we have just 550. Now we want to, if we want to list compounds that contain chromium or manganese and 3 species. So now we have chromium, and then the colon is or, so chromium or manganese. So now we expect to see a lot more. So now we have even more. And now you can see again, we have the same ones as we had before, chromium. Now we want to do something a bit more complicated. We want to look for ones that contain chromium and selenium, or chromium and tellurium, or 3 species. So here we're looking chromium and either selenium or tellurium and 3 species. So again, search. And now we can see that again, we get ones now with chromium and selenium and so on. If we look later, we'll see that we see some other ones. But here we have cadmium, chromium, and selenium. Probably if you go down to the end, you probably see ones with tellurium as well. Okay, now we'll go through this loose operator that allows us to search for value ranges. So if we do without any kind of loose operator, if we just put EGAP here, so here we're looking for band gaps for all the quaternary compounds with n species. So we want to quaternary compounds, which means we want to have n species is 4, and then EGAP. So here we're just retrieving band gaps of everything. We're not doing any filtering at all. And what happens is that if you do no filtering at all, and if you don't restrict the catalog to ICSD, so you're looking over the entire database, you'll find out that a lot of the entries don't actually have band gaps. The band gap has not actually been calculated. So for example, if we look at this first entry and we look for the value for EGAP, we see that it's null. So if we see null in this, it just means that the value is not available. So for this particular entry, we haven't actually calculated the band structure, which means we haven't calculated the band gap. So now if we want to restrict this, so we want to filter so we only show non-null results, we can do this using this wildcard operator. So if we just put the star on its own in parentheses after this EGAP, we can do a search. And now, so here we had something like 50,000 results. So here you'll see that we see much fewer, we only get 8,000 results. And we can see our first entry, we actually do have a value for the EGAP. So in this case, EGAP is 0, which means the material is metallic. So now we want to only show results where the EGAP is greater than or equal to 1 electron volt. So this is really where the wildcard operator starts coming in. So here, if we put 1, And then if we put a star after the 1, that means 1 or greater than 1. So again, we can do this search, and then we can find materials with the band gap greater than 1 electron volts. Now, if we want to look for a range, so this time we want to say between 1 electron volt and 3 electron volts. We have greater than 1 electron volt, so 1 star, and we have less than 3 electron volts. So this time the star comes before the 3. So you have 1 star, comma, star 3. So it's between, so greater than 1 electron volt, greater than equal to 1 electron volt, and less than or equal to 3 electron volts. But then we do the search again. And again, we get the values. And now you should see that everything here is between, just so here you get some, it's listed from smallest to largest. So we're always listed in ascending order. And we'll show you how to change the order in a second. But again, we see the smallest values first. We go to the very end, we see the largest values. So I see larger values. Now, as I mentioned before, we can also do string comparison searches. So in this case, every entry in the AFLOW database has a unique identifier that's based on a hexadecimal hash of the output file. So we use this to generate a unique identifier for each output file, for each entry in the database. So if you want to search for an entry with a particular unique identifier, you can use a string comparison to do this as so. So you search for the AUID, so the AFLOW unique ID with this string, and you can do a specific search for this one specific entry. You can also use that, as I mentioned before, we have a mute operator. So this is represented by this $sign. So we can do a filter. So here we want to see things that are a band gap equal to 0 and then species equal to 4, but we don't actually want to return this data in the output. So we can do search from this. So again, you can see now in our results, even though we filtered on these values, we don't actually see the values in the results. You can also mute default properties. So this is something that's quite useful because, as you can see, there's quite a lot of properties that are returned by default that you might not be interested in. So you can mute them. For example, here we're going to mute the AUID. And now you can see that the AUID is not contained in the returned results. And finally, I'm going to talk about the paging directive. So here, if we want this, before we were always using paging 1, so that showed the first set of 64 entries. Now, if we want to look at, let's say the 5th page of this 5th set of 64 entries, we can again do our search. So band gap between 1 and 3 electron volts. And we'll see that now that we get larger values for the band gap. So because we're looking at a higher range. So here again, because we're starting from now from 257, because 4 by 64 is 256. So we're starting from 257 because we're on the 5th page, and now we have larger E gaps. Now we're E gap is up into 1.24, 1.204. We can also change the page size. So for example, so in this case, as well as including the page number, if you include an extra additional term, that's the page, that will be the page size. So now we have 100 entries per page. So now you'll see that it should start at 401. And then it should return the entries from 401 to 500. So now we're looking at 100 entries at a time. Then we can return the results as an array. So instead of returning the results as a JSON object, we return it basically as a list by muting the paging operator. So if you put a $sign for the paging operator, you can see instead of having curly bracket here with some information on the number, so instead of this being sort of like a Python dictionary looking thing, you'll end up with more like basically something that looks more like a Python list. So if you mute the paging. And then you can also have the option of returning all the entries. So instead of just returning a subset of the entries at a time, you can return all the entries in one go by setting paging 0. This you have to be kind of careful with, because especially if there's a lot of entries from a particular query, it might just crash your machine if you get too much data at one go. Okay, so now we get all 3,000 entries in a row. We can also do sorting. So the default, as before, was always to sort in ascending order. So basically, you get the smallest values first. So it sorts from the smallest. So in this case, it sorts by the first, whatever is in the first argument here that's actually numerical that I can actually sort on. So here you're seeing that you're getting the small value first. You're getting something that's just a little over 1 electron volt. But you can also have the option of sorting in descending order. So if you put the paging number as being negative, -1, this tells it to sort in descending order. But you still look at different pages, so paging -2, paging -3, etc. And I will show the third page in descending order. So now we should get the ones with the largest band gap first. So now we're getting things with close to 3 electron volts first. Results are always sorted by the first property. So in this case here, we were sorting by electronic band gap. And here we also get a returning value as a spin atom. But if we swap the spin atom and electronic band gap around, we'll sort by instead of an order of spin atom. So the other thing we can do is if we want to search for groups of elements, so instead of if you want to search for a whole set of elements, instead of like I was showing you before, so let's say you want to search for all the alkali halides or methyl chalcogens, you can actually look, you have groups of elements that you can sort by, so you can chalcogens and metals. I'll show you how to, I'm going to switch back to slides for a second, just to introduce this concept. Showing the PowerPoint. Okay. So say, for example, we want to look for all the materials with a zinc blende structure with a metal and a chalcogen. So all the metal chalcogens in the zinc blende structure. So we have our space group, we have our Pearson symbol. But in principle, if we want to look for all the different species, N species is 2. Then we'd have, on one side, we have all our different chalcogens, so oxygen or sulfur or selenium or tellurium. So that's not too bad. But then if we want to look for all the metals, we'd have to list all the metals out in one go. And this is obviously kind of tedious to type in. So instead, what we can do is we can do a shorter query with aliases. So here's the sum. So here you have chalcogens and metals. And here are some of the supported aliases. So again, you can see them as well on the, if you go to the AFLUX search page, you can see also that you have these options to do these aliases. So you have metals, transition metals, boron group, chalcogens, and so on. But one thing to be aware of is these are case sensitive. So in this, for example, if you want to do alkaline metals, it's very important that the A and the M are uppercase and the rest are lowercase. Okay, so with that, let's go back to the Colab notebook. And show you the examples. So here we have our example for chalcogens and metals. Again, with our zinc blende space group, and then species is 2. We do a search. Takes a minute, and there we get all the different possible entries that are inside the AFLOW database. Okay, so as I mentioned before, we can use Python scripts. So here's a sample Python script to query the AFLUX server. So in this case, we're looking for, again, this example of sodium or potassium and chlorine. N species is 2. The electronic band gap is between 2 and 5 electron volts. And then we're looking for information on the energy per cell. And here we're returning paging is 0. But note that we have muted the paging so that we have, and we're turning all the entries. So this was going to return it as a list. So basically we look at the structure of our Python script. We have our server, we have our API, we have our matchbook, we have paging. Then we construct our summons, which is the matchbook and the derivatives. Then we have our URL in here, which is server plus API plus summons. So then it queries this, it gets back the JSON response, it loads it, converts it into a Python list and with a list of dictionaries basically. And then for that then it runs through this response. For each element of response, it extracts out the relevant data. So here we're extracting out the one with EGAP. So that you have data points with EGAP, with the keyword EGAP, and then you have the energy per cell. And then at the end, we just print out the results for the AUID, band gap, and the energy per cell. So then at the end, we have some more exercises. So again, we're going to do this. I have the Python script already inside if people want to try it. You basically just have to construct the matchbook and the directives. And then you need to copy in this, run over to copy and paste this bit in, and then modify it to get the appropriate response. So the first part is we want to find the VRH bulk moduli. So this using this keyword. So if we want and you want to look inside the ICSD catalog, so catalog ICSD, you want to find the VRH bulk modulus for materials containing titanium, so species titanium, in the AFLOW database. So then we want to list it, we should want to list it in this descending order, so use the minus thing to see which one is the highest. And then we want to see what the Bravais lattice type is and the space group is. I want to also see the EGAP type, so is it a metal or an insulator? So that's the first exercise. The second exercise then is to determine the bulk moduli of all binary materials in the AFLOW database with a transition metal and a chalcogen and a band gap between 1 and 3 electron volts. For the 5 compounds with the lowest bulk moduli, list the chemical formula, space groups, bulk moduli, and band gaps. So again, you have a Python script that we can modify. Then at the end, narrow the choice of transition metals down to iron, nickel, and cobalt. Determine the 5 compounds with the largest magnetic moments per atom, spin atom, and list their chemical formulae, space groups, bulk moduli, and magnetic moments per atom. So I'm going to leave this up for a few minutes and let you work on it. And let's take about, again, we're running a bit slow, so let's take about 5 minutes for this, and then we'll come back and we'll run through the examples. And I'll just leave this screen up. So there was a question in the chat, so Corey answered it, but I'm going to add a bit to it. So how is the AFLOW database different from other databases like Materials Project? So again, historically we focus, like right now, as Corey just mentioned, we have a sort of focus on disordered materials. So we've done a lot of work on sort of high entropy alloys, high entropy ceramics, metallic glasses, these sort of materials. So we tend to look at generating a lot of hypothetical materials across a wide range of different systems. We've also historically focused a lot on alloy systems. Materials Project tend to focus a lot. They've had a very strong historical focus on battery materials. So they tend to focus on they've historically tended to focus on a more limited set of materials, but sometimes they go into more detail on those materials. So that's sort of a difference between AFLOW and Materials Project. Then there's other databases that tend to, like there's the Materials Cloud database, tend to focus a lot on 2D materials. There's the Nomad database, which is more like an aggregator of different databases, and so on. So each database has their own sort of specific focus. There's a lot of overlap between the databases, but individual databases do tend to have their own specific focus. Okay, I'll take a couple of more minutes and then we'll start working on the exercises. Okay, so there's a question about where can you find a list of all available databases? So I'm not sure exactly what you mean by this. In our case, we're basically just showing the AFLOW database. That's the one we develop and maintain. There are other available databases out there. One thing you can look for if you want to get an idea of what other databases are out there is there's a thing called the Optimad Consortium. And they sort of work on sort of a common API for all of the databases. It's a pretty good place to look if you want to see some of the different materials databases that are available. That's sort of a reasonably good central repository. Corey, maybe you can put the link to the Optimad paper in the chat if you can find it. Because there's also quite a lot of small databases that are popping up now as well. Okay, so now I'm just going to get started on the exercises. So on the first one, exercise here, we want to look at the, so we want to find the material find the bulk modulus for materials containing titanium in the AFLOW database. So we want to build up our matchbook. So we have species, it's going to be titanium. We want to have our VRH bulk modulus. So we want to list it in order of this. VRH. So we want to find, only return the material to have it calculated. Species is titanium. And we want to get the, also want to get information on the Bravais lattice relax. And we want to get information on the gap type. Then we want to do our paging. And we want to have -0. Let's return all the entries and we want to mute it. And then we look at, we print out the results. So let's copy this. So let's call this bulk mod. We want to get the relax. Let's Bravais. What else do we want to do? Relax. Bulk mod. Bravais. What else do we want? The gap type. We also want to print out the compound name. We have 5, 1, 2, 3, 4, 5. So here you can see we've written out a search query and we have a mistake. What we're missing. Okay, so here you can see we're writing out our results. So here we're writing out a bulk modulus. Okay, let's write these again. So that's slide effect. Okay, now we can see it. Okay, let's go back up to the first entry. So here we have the highest value. So we can see here the space group is 221. It's iridium and titanium. The bulk modulus is 289 gigapascals. It's a simple cubic and it's a metal. So now we want to try the next one. Bulk moduli of all binary materials. So let's copy this and start modifying it. Bulk modulus of all binary materials with a transition metal and a chalcogen. So here's species. Transition metal and chalcogen. A band gap between 1 and 5 electron volts. So we got 1 star, comma 5 star, star 5. Okay. So then side push. We want the ones with the lowest bulk moduli. So let's do hydrogen. So we want the bulk modulus. We don't care about the Barbados this time. We want the E gap. This. Then we have the E gap. So we want the band gap, chemical formless, space group, and band gaps. Okay, so we'll wrap up on this one because we're running low on time. So it's space group, compound, bulk modulus, and E gap. E gap and Bravais lattice. And then we'll hit the run button. And grab some of these here. Okay. Okay, anyway, yeah, if people have questions, we can come to it later. I think I have another one I've opened up earlier where I can show people later on. But yeah, you can see it in general how this works. So let's just go back to the slides and then wrap up. Let me stop sharing this, bring up my slides. And then we'll just wrap up very quickly so we can move on to the next lecture. So just in addition to this, and David Hicks will be showing you this a little bit next, We'll show you how AFLOW can be used on, so you can also download the AFLOW code itself. Do a lot of the kind of work that David is trying to show you in the next slides. It can be installed on Linux, Mac, or Windows. It requires some additional software. So for example, if you want to run it on Windows, you should either install Windows Subsystem for Linux on Windows 10 or Cygwin for other Windows version. And for instructions on installation scripts, you can visit aflow.org/install-aflow. You can also configure AFLOW with this aflow.org file, and you can get more information on these settings by running aflow --readme equals aflow.org. Okay, so with that, I'm going to wrap up. I'm going to pass over to Dr. Hicks.